Welcome to the lecture on partial fractions. The goal of this section is to introduce the method of partial fractions for integrating rational functions. When combined with standard and trigonometric substitution, this method allows us, in principle, to integrate any rational function. Let's first talk about the method of partial fractions. So let's consider the following. We have this function f of x equals 1 over x minus 2 plus 2 over x plus 4. Of course, it's easy to find a common denominator. We can multiply the 1 over x minus 2 by x plus 4 over x plus 4, and then the 2 over the x plus 4, we can multiply this by x minus 2 over x minus 2. This, of course, will give us x plus 4 plus a 2x minus 4 all over x minus 2 times x plus 4, which this, of course, gives us 3x all over x squared plus 2x minus 8. The purpose of partial fractions is to reverse this process. Given a rational function that is difficult to integrate, the method of partial fractions produces an equivalent function that is much easier to integrate. So here, let's take a look at that rational function that we had on the previous page. So we had 3x all over x squared plus 2x minus 8. Here, the method of partial fractions will give us what's known as a partial fraction decomposition. Which in turn becomes 1 over x minus 2 plus 2 over x plus 4. Now, of course, it's difficult to integrate the integral of 3x all over x squared plus 2x minus 8 dx. But here, on this side, it's easy to integrate. It's easy to integrate 1 over x minus 2 plus 2 over x plus 4 dx. The key idea in this section will be working with the same fraction that we had before, the f of x equals 3x all over x squared. I should say it this way. X minus 2 into x plus 4. Our objective is to write it in the form a over x minus 2 plus b over x plus 4, where a and b are just constants to be determined. This expression right here is called the partial fraction decomposition of the original function. In this case, it has two terms, one for each factor in the denominator of the original function. The constants a and b are determined using the condition that the original function f and its partial fraction decomposition must be equal for all values of x in the domain of f. So that is, if we take 3x all over that x minus 2 times the x plus 4, then this is equal to a over x minus 2 plus b over x plus 4. Now, if we multiply both sides by the x minus 2 times the x plus 4, this will give us 3x equals a into x plus 4 plus b into x minus 2. Which, if we simplify this, this will be 3x equals ax plus 4a plus bx minus 2b. Make that a nicer b. Which this becomes 3x equals a plus b times x plus 4a minus 2b. If this equation is to hold for all values of x, then two things must be true. The coefficients of x to the first power on both sides of the equation must be equal, and 2, the coefficients of x to the 0 power, that is, the constants on both sides, must be equal. So in other words, what I'm saying is the following. If you have 3x, and I'll put a 0 in here, that equals the a plus b times x plus the 4a minus the 2b, okay? These here and the 0 here must be equal, and also the AB and the 3 must also be equal. So this observation leads to two equations for A and for B. So if we equate the coefficients, for x1, we're going to get that 3 equals a plus b, and if we do the exact same thing for x0, we're going to get that 0 equals 4a minus 2b. So, if we label this as equation 1, and this one as equation 2, equation 1 is going to tell us that a equals 3 minus b, and substituting this into equation 2, this will give us that 0 equals 4 into 3 minus b minus 2b, which will give us 0 equals 12 minus 4b minus 2b, which is going to be the same thing as saying 0 equals 12 minus 6b, which implies we have 6b equals 12, or b equals positive 2. So we can say as the following, that a is equal to 3 minus 2, or just 1. So what we can say is that 3x over the x minus 2 times the x plus 4 is simply going to be equal to 1 over x minus 2 plus 2 over x plus 4. Okay, so now let's take a look at simple linear functions, or simple linear factors. The previous example illustrates the case of simple linear factors. This means the denominator of the original function consists only of linear factors of the form x minus r, which appear to the first power and no higher power. Here's the general procedure of this case. So what we're going to do is we're going to suppose that f of x is equal to p of x over q of x, where p of x and q of x are polynomials with no common factors. And the degree of p of x is less than the degree of q of x. And of course, q of x is not equal to 0. We're also going to assume that q of x is the product of simple linear factors. So the partial fraction decomposition is obtained by the following. So step 1. We're going to factor the denominator that's going to be q of x in the form x minus r1 times x minus r2 all the way to x minus r to the n, or x sub n, where r1 all the way to rn are real numbers. Step 2, partial fraction decomposition So we're going to basically form the decomposition by writing P of x over Q of x equals A1 over x minus R1 plus A2 over x minus R2 plus AN over x minus Rn. Step 3, we're going to clear the denominators. So basically what we're going to do is we're going to multiply both sides of the equation in step 2 by Q of x equals x minus R1 times x minus R2 all the way to x minus Rn, which produces conditions for A1, A2, all the way to AN. In step 4, we're going to solve for the coefficients and equate like powers of x in step 3 to solve for the undetermined coefficients of A1, A2, all the way to AN. Okay, let's take a look at an example on how this works. So let's find the partial fraction decomposition of f of x equals, let's say, 3x squared plus 7x minus 2 over x cubed minus x squared minus 2x. Okay. So in step 1, let's first factor out the denominator. So we have x cubed minus x squared minus 2x. This is the same as saying x into x squared minus x minus 2, which of course is equal to x into x plus 1 times x minus 2. Here, if you notice, we only have simple linear factors. Okay, step 2. Let's take the 3x squared plus the 7x minus 2 all over x cubed minus x squared minus 2x. And let's rewrite it this way. We'll have a over x plus b over x plus 1 plus c over x minus 2. So one term for each factor in the denominator. Step 3, we're going to multiply both sides by x into x plus 1 times x minus 2. Okay, so we're going to get 3x squared plus 7x minus 2 equals a into x plus 1 times x minus 2 plus b times x minus 2 plus c times x plus 1. So this is going to be equal to a into x squared minus x minus 2 plus b into x squared minus 2x plus c times x squared plus x. Which this, let's see, this is going to be equal to ax squared minus ax minus 2a plus bx squared minus 2bx plus cx squared plus cx, which this is going to be equal to a plus b plus c times x squared plus negative a minus 2b plus c times x plus negative 2a. Okay. So now, in step 4, we're going to equate the coefficients of the x squared, the x to the first, and the x0 on both sides of the equation in step 3. So, let's see, we're going to equate coefficients of x squared. So that's simply going to be a plus b plus c equals 3. Do the same thing for x to the first. We're going to get negative a minus 2b plus c equals 7. And then for x to the 0 power, that will simply be negative 2a equals negative 2. Now, of course, out of this equation, I can simply say that a equals positive 1. So if I substitute a equals negative 1 back in for this equation and also for this equation, I'm going to end up with the following. I'm going to have 1 plus b plus c equals 3, and of course negative 1 minus 2b plus c equals 7. This one, of course, is the same thing as saying b plus c equals 2, and this one is the same as saying negative 2b plus c equals 8. So now if I solve both of these little equations for b and for c, let me just do this on the next slide, So I do have b plus c equals 2 and negative 2b plus c equals 8. So if I multiply, for example, this equation by negative 1, this equation just becomes b plus c equals 2. This equation now becomes 2b minus c equals negative 8. And now if I add these two equations up, I'm going to get 3b equals negative 6. So of course b is going to be equal to negative 2. And if I substitute b equals negative 2 back in any of these equations, let's just substitute it back in for this one, I'm going to get that negative 2 plus c equals 2, so c is going to be equal to positive 4. So what I can say is that this function f of x can be broken down to be 1 over x minus 2 over x plus 1 plus 4 all over x minus 2. So now that I have the decomposition, I can now find the integral of 3x squared plus 7x minus 2 all over x cubed minus x squared minus 2x dx. I know what my decomposition is by partial fraction, so this will be the integral of 1 over x minus 2 all over x plus 1 plus 4 all over x minus 2 dx. The first one is just going to give me the natural log of the absolute value of x, minus the second one will give me 2, the natural log of the absolute value of x plus 1, and the last one will give me plus 4, the natural log of the absolute value of x minus 2, plus my arbitrary constant of c. Of course, this is the exact same thing as saying, if we condense everything down, this is the exact same thing as saying the natural log of the absolute value of x minus the natural log of x plus 1 squared plus the natural log of x minus 2 to the fourth plus our arbitrary constant of c. This, of course, becomes the natural log of the absolute value of x over x plus 1 squared plus the natural log of x minus 2 to the fourth plus c. And, of course, this becomes the natural log of the absolute value of x times x minus 2 to the fourth all over x plus 1 squared plus your arbitrary constant of c. Okay, let me give you all a shortcut. Solving for more than 3 unknown coefficients in a partial fraction decomposition may be difficult. In the case of simple linear factors, a shortcut saves some work. Remember that we had 3x squared plus 7x minus 2, and we said that's equal to a times x plus 1 times x minus 2 plus the bx into x minus 2 plus the cx into x plus 1. So here, since this equation holds for all values of x, it must hold for any particular value of x. By choosing the values of x wisely, it's easy to solve for the coefficients of, or the constants of a, b, and c. Here, if we set x equal to 0, we're going to get that negative 2 equals negative 2a. That, of course, we know a equals 1. If I set x equal to negative 1, I'm going to get negative 6 equals 3b. Of course, b is going to be equal to negative 2. And then if I set x equal to 2, I'll get 24 equals 6c. c is going to be equal to positive 4. So you can use this trick. Let's try to look at another example using the shortcut. So let's say I want to find the integral of 5x squared minus 12x minus 12 all over x cubed minus 4x dx. Okay. I can rewrite this to be the integral of 5x squared minus 12x minus 12 all over x into x minus 2 x plus 2 dx. So let's do some work on this side. We have that 5x squared minus 12x minus 12 over x into x minus 2x plus 2. That's going to be equal to a over x plus b over x minus 2 plus c over x plus 2. So when you multiply both sides by this x times x minus 2 x plus 2, you're going to get that 5x squared minus 12x minus 12 is simply going to be equal to a into x squared minus 4 plus bx into x plus 2 plus cx into x minus 2. So now if we do some substitutions, if we say when x equals 0, we're going to get that negative 12 equals negative 4a. So therefore, a is going to be equal to positive 3. When x equals positive 2, we're going to get that negative 16 is equal to 8b. So b is going to be equal to negative 2. And then, of course, when a equals negative 2, we're going to get that 32 equals 8c. So c is going to be equal to positive 4. So therefore, we have that this integral is now going to be equal to 3 over x minus 2 over x minus 2 plus 4 over x plus 2 dx. This is simply going to be equal to 3, the natural log of the absolute value of x, minus 2, the natural log of x minus 2, plus 4, the natural log of x plus 2, absolute value, of course, plus your arbitrary constant of c. Now, like a fraction, a rational function is said to be in reduced form if the numerator and the denominator have no common factors. And it is said to be proper if the degree of the numerator is less than the degree of the denominator. Let's take a look at this example. Let's say we have the integral of x cubed plus 1 over x squared minus 4 dx. Now, we note here that this is not a proper fraction, since the degree of p, the numerator, is bigger or equal to the degree of the q of x function, which is the denominator. So what we need to do is we need to long divide. So let's long divide. We have x squared minus 4 into x cubed plus 0x squared plus 0x plus 1. So x squared goes into x cubed x times x squared becomes x cubed. X times negative 4 becomes negative 4x. So if we switch the sign here and here, these two of course cancel out, we're going to be left with a positive 4x. We're going to bring down the positive 1. So now x squared goes into 4x. Sorry about that. So we can now rewrite our integral to be the following. So we have x cubed plus 1 over x squared minus 4. That's simply going to be equal to x plus 4x plus 1 all over x squared minus 4. And of course this is the exact same thing as saying x plus 4x plus 1 all over x minus 2 times x plus 2. Okay, so now we need to figure out what that turns out to be. So we have 4x plus 1 all over x minus 2 x plus 2. We're going to say that's equal to a over x minus 2 plus b all over x plus 2. And of course if we multiply by x minus 2 and x plus 2, we're going to end up with 4x minus or plus 1 equals a into x plus 2 plus b into x minus 2. So of course when x equals positive 2, we're going to get 9 equals 4a. So of course a is going to be equal to 9/4. And of course when a equals negative 2, we're going to get negative 7 equals negative 4b. So b is going to be equal to 7/4. Okay. So now this is going to be equal to the integral of x plus 9/4 over x minus 2 plus 7/4 all over x plus 2 dx. So finding the antiderivatives, we're going to get 1/2 x squared plus 9/4 the natural log of the absolute value of x minus 2 plus 7/4 natural log of the absolute value of x plus 2 plus an arbitrary constant of c. Okay, let's talk now about repeated linear factors. In the preceding discussion relies on the assumption the denominator of the rational function can be factored into simple linear factors of the form x minus r. But what about denominators such as x squared into x minus 3, or maybe even x plus 2 squared times x minus 4 cubed, in which linear factors are raised to integer powers greater than 1. In these cases, we have repeated linear factors, and the modification to the previous procedure must be made. So let's take a look at what the modification should be. So, modification. Okay, Suppose the factor of x minus r to some power m appears in the denominator where the m is strictly bigger than 1 as an integer. Then there must be a partial fraction for each power of x minus r up to and including the mth power. So for example, if you have x squared into x minus 3 to the 4th, let's say that appears in the denominator, then the partial fraction decomposition includes the terms a over x plus b over x squared plus c over x minus 3 plus d over x minus 3 squared plus e over x minus 3 cubed plus f over x minus 3 to the 4th. The rest of the partial fraction procedure remains the same, although the amount of work increases as the number of coefficients increases. So let's take a look now at the procedure. So suppose the repeated linear factor of x minus r to the m appears in the denominator of the proper rational function in the reduced form. The partial fraction decomposition is a partial fraction for each power of x minus r up to and including the mth power. So that is, the partial fraction decomposition contains the sum a1 over x minus r plus a2 over x minus r squared plus a3 over x minus r cubed plus all the way up to am over x minus r to the mth power, where a1, a2, and am are constants to be determined. Okay, let's get into an example. So say we want to evaluate the integral of 5x squared minus 3x plus 2 all over x cubed minus 2x squared dx. Okay, well, x cubed minus 2x squared is the same as saying x squared into x minus 2. So what we can say, and I'll just get rid of the integral just for the time being, we have 5x squared minus 3x plus 2 all over x cubed minus 2x squared. That's going to be equal to a over x plus b over x squared plus c all over x minus 2. So if we multiply both sides by the x squared times x minus 2, we're going to get that 5x squared minus 3x plus 2 is going to be equal to ax into x minus 2 plus b into x minus 2 plus cx squared, which of course is going to be the same as saying ax squared minus 2ax plus bx minus 2b plus cx squared, which is going to be equal to being a plus c times x squared plus negative 2a plus b x minus 2b. Okay. So now, if we equate the coefficients for the x squared, we're going to get that a plus c equals 5. Equate them for x to the first, we're going to get that negative 2a plus b is equal to negative 3. And for x0, be negative 2b equals 2. So here, we're going to get that b equals negative 1. And if b equals negative 1, a is going to be equal to positive 1. And then if a equals 1 and b equals negative 1, c is going to be equal to positive. So we can say as the following. We can say that the integral of 5x squared minus 3x plus 2 all over x cubed minus 2x squared dx is simply going to be equal to the integral of 1 over x minus 1 over x squared plus 4 all over x minus 2 dx. To find the antiderivative is very, very simple. This would be natural log of the absolute value of x plus 1 over x plus 4 the natural log of the absolute value of x minus 2 plus c, which this is the same as saying 1 over x plus the natural log of the absolute value of x times x minus 2 to the fourth, plus your arbitrary constant of c. Okay. Now let's talk about irreducible quadratic factors. By the fundamental theorem of algebra, we know a polynomial with real-valued coefficients can be written as a product of linear factors of the form x minus r and irreducible quadratic factors of the form ax squared plus bx plus c, where of course a, b, and c are real numbers. The ax squared plus bx plus c is called irreducible. That means that it has no real roots, and it can't be factored over the real numbers, provided if b squared minus 4ac is strictly less than 0. So basically when the discriminant is less than 0. With irreducible quadratic factors, two cases must be considered. And the two cases are simple and repeated factors. So the procedure is the following. Suppose you have a simple irreducible factor as ax squared plus bx plus c. Let's say that this appears in the denominator of a proper rational function in the reduced form. The partial fraction decomposition contains a term of the form ax plus b all over ax squared plus bx plus c, where a and b are unknown constants to be determined. So let's get into an example on how we work with this. So here's an example. Let's find the integral of 2x squared minus x plus 4 all over x cubed plus 4x dx. Now, if we take a look at x cubed plus 4x, of course, we can factor this to be x into x squared plus 4. And if you notice here, this x squared plus 4 can't be factored further. So what we say is the following. We have the 2x squared minus x plus 4 all over x cubed plus 4x. That's going to be equal to a over x plus bx plus c all over x squared plus 4. Now, again, if we multiply by x into x squared plus 4, we're going to get that 2x squared minus x plus 4 is going to be equal to a into x squared plus 4 plus bx plus c times x, which is going to be equal to ax squared plus 4a plus bx squared plus cx, which is going to be equal to a plus b times x squared plus cx plus 4a. Make this C a little bit nicer. There we go. Okay, so now if we do the process of equating, let's do it on the next page here. So when we're equating, we have a plus b equals 2, we have c equals negative 1, and we have 4a equals 4. So what we can say is we have a equals positive 1, b equals positive 1, and c equals negative 1. So what we have is the following. We have that this becomes the integral of 1 over x plus x minus 1 all over x squared plus 4 dx. Now we have to figure out what the integral of that rational function is. Let's do this on the next slide. So we want to find the integral of x minus 1 over x squared plus 4 dx. Well, this is the same as saying the integral of x over x squared plus 4 dx minus the integral of 1 all over x squared plus 4. It's a bad plus there. That's better. Dx. Now, of course, for this first one, we can do u substitution. So we can say u equals x squared plus 4. So du will be equal to 2x dx, or just 1/2 du equals x dx. So this one here will be 1/2 the integral of 1 over u du, which will simply be 1/2 the natural log of the absolute value of x squared plus 4. And of course we don't even need the absolute values here because x squared plus 4 is always positive, so we can simply put this is in parentheses. Okay, so that's the antiderivative of that one. This one here, you have to realize this is the same as saying the integral of 1 over x squared plus 2 squared dx. And this, of course, becomes an inverse tangent. So this becomes 1/2 tan inverse of x over 2. So, putting everything together, we're going to have that the integral of 2x squared minus x plus 4 all over x cubed plus 4x dx is going to be equal to the natural log of the absolute value of x plus 1/2 the natural log of x squared plus 4 minus 1/2 the tangent inverse of x over 2 plus an arbitrary constant of c. Okay, we have one more topic to talk about, and that is the repeated irreducible quadratic factor. Okay, so for each factor that's of the form ax squared plus bx plus c raised to some power of n, the partial fraction decomposition must include the following sum of n factors. So we have b1x plus c1 all over ax squared plus bx plus c plus b2x plus c2 all over ax squared plus bx plus c squared plus all the way up to bnx plus cn all over ax squared plus bx plus c raised to the power of n. Let's take a look at an example of this. So let's say we want to evaluate the integral of 1 minus x plus 2x squared minus x cubed all over x into x squared plus 1 squared dx. Well, let's take this 1 minus x plus 2x squared minus x cubed all over that x into x squared plus 1 squared. We can rewrite this to be a over x plus bx plus c all over x squared plus 1 plus, I'll say, dx plus e all over x squared plus 1 squared. Okay. So now if we multiply both sides again by the x into x squared plus 1 quantity squared, we're going to get that negative x cubed plus 2x squared minus x plus 1 is going to be equal to a into x squared plus 1 squared plus bx plus c times x squared plus 1 plus a dx plus e times x. And of course, this is equal to ax to the fourth plus, let's see, 2ax squared plus a plus bx to the fourth plus bx squared plus cx cubed plus a cx plus a dx squared plus an e times x. Okay. So now this is equal to, let me go to the next slide with this. This becomes a plus b x to the fourth plus cx cubed plus, let's see, 2a plus b plus d x squared plus, let's see, c plus e x plus a. Okay. So now if we equate, let's see, I believe we're going to get a plus b equals 0. We'll get c equals -1, that's nice. We'll get 2a plus b plus d equals 2. C plus e equals -1. And a is going to be equal to 1. So let's see, if we start solving everything, I think what we're going to get is that a equals 1. Let's see, b should equal -1, c should be equal to -1, d should equal 1, and e should be 0. Okay, so I found all my constants here. So what I can do is I can say I have the integral of 1 over x minus x plus 1 over x squared plus 1 plus x over quantity x squared plus 1 squared dx. So let's see, I can rewrite this to be the integral of 1 over x dx minus the integral of x over x squared plus 1 dx minus the integral of dx over x squared plus 1 plus the integral of x all over x squared plus 1 squared dx. And I wrote it this way because I know that I can split this guy up to be these two integrals. Okay. So now let's see what we get in terms of the antiderivatives. So this first one will give me the natural log of the absolute value of x. The second one, using u substitution, half the natural log of x squared plus 1. Next one we have to realize turns out to be an inverse tangent, so tangent inverse of just x. And then this one, using a u substitution with x squared plus 1, I believe that's going to give us minus 1 over 2 x squared plus 1 plus your arbitrary constant of c. Okay, I know this was a long video, but partial fractions is a very, very detailed section, so I hope that this introductory video gave you some good ideas of what partial fractions are, how we can handle them. Of course, when we come back to class, you'll be given some more examples by me, and we'll work out some more examples together as a class. All right, see you then.